Just what are digital computers? Are they superhuman machines that can solve any kind of problem? No, not any kind. Are they man-made monsters that perform mathematical miracles in millionths of a second? No, nothing miraculous at all, nor monstrous. Are they electronic brains that can do man's thinking for him? Well, they can do some of it and be big and quick about it, too. Large computers can remember and keep tab on millions of bits of data and fetch and use any of them in a fraction of a moment. And computers operate faster than, well, how many human beings using desk calculators would you say? 100? 1,000? More than that? Yes, 500,000. Yet, as complicated as they might appear, digital computers are basically simple, a collection of ideas and principles that are not at all difficult to understand. Nor are they very new. Here is the first computer man ever used. It was the first digital computer. Indeed, the word digit comes from the Latin word for finger. Used in counting, then, digits became numbers. To keep track of numbers or to count higher, man used stones. We still use the Latin word for stone, calculus, and the first calculating device may have looked like this. With it, you could count your sheep, your children, your prayers. In fact, the Anglo-Saxon word bead meant prayer. When man put up his counting beads like this, he grouped them like the digits of his hand, with the extra beads counting the number of fives. The abacus, used by all civilizations of antiquity, is still a widely used counting or accounting device. 350 years ago, a Scottish scholar, preacher, and mathematician named John Napier invented these ivory calculating bones, as they were called. This is one of the original sets. They were used for multiplication. A few years later, the French genius Blaise Pascal invented and built the world's first mechanical adding machines. This is one of them, made in the 1640s. Pascal's achievement lay in the gear mechanism, which automatically took care of carryovers. For example, 6 plus 9 has the 1 carried over to the next place. Also in the early 1600s, an Englishman, William Oughtred, put together 2 logarithmic scales like these and made the form of slide rule we use today, an indispensable 300-year-old tool. In every area of defense, science, engineering, and business, progress depends on the availability of fast, accurate methods of calculation. They have enabled us to take giant steps forward in power, in control, in design, in processing, and in research. Our 7-league boots are our calculating machines, and they come in many styles. In some, the action is entirely mechanical, using levers, linkages, gears, and ratchets to perform the calculating operations. The method used here is digital. That is, the machine works with digits, actual numbers. In this type of calculator or computer, the action is electromechanical. It makes use of servo motors, potentiometers, cams, friction drives, and similar devices. They are moved or set so that shaft positions, voltages, angles, lengths, and other physical quantities represent the numbers involved in the calculations. Since equivalents, or analogs of numbers, are used rather than numbers as such, these types of machines are called analog computers. In this type of computer, the action is entirely electronic and completely automatic. The working parts are transistors, vacuum tubes, magnetic devices, and other electronic components. The machine works with actual numbers and is therefore a digital computer. This film is concerned with this type of computer, and its purpose is to present a general introduction to the subject. The computer process is a logical one and is easy to follow. It begins with the problem, which may concern virtually any subject that can be treated mathematically. Determining the path and time positions of an orbiting satellite. Computing payrolls for thousands of employees. Equalizing the load in a power transmission network. Controlling airport traffic. Forecasting the weather. Or designing a missile and its system. Whatever it is, you have the problem, and you have data or information which the computer will process to arrive at a solution. To do this processing, the computer needs instructions. So you write a program, a complete, detailed list of every operation the computer must perform to solve the problem. Then, the completed program, that is, the instructions, and the data, the information to be worked on, are both prepared for insertion in the computer by transferring them to an input medium. This may be punched cards, punched paper tape, or magnetic tape for automatic insertion, or a typewriter for manual inputs. The medium carries the inputs in code language acceptable to the computer. The computer first stores the program and the data, and then processes the data as directed by the program. The results of the computer's work are transferred to an output medium, such as punched cards, punched tape, or magnetic tape, that presents the data in computer language. Or the medium may be a printer that presents the output in readable form. Thus, the solution is the completion of the process that began with the problem and the data. These elements are pertinent to all automatic digital computer systems. Now let us look at the functions performed by the computer. It has the ability to add, which it does by counting, to subtract by counting in reverse, and to multiply and divide, operations that are based on addition and subtraction. These are the computer's arithmetical operations. It can also perform what are known as logical operations. It can compare one number with another. It can sort numbers into a particular order. It can find a specific number. And it can do such things as distinguish between positive and negative signs. Thus, the computer can make simple decisions or choices, but only as instructed. It operates on the basis of simplicity in the mathematical functions performed, multiplicity in the number of times these may be done, and speed that is fantastic. It is accomplished electronically by means of transistors, semiconductor diodes, and vacuum tubes. Such devices have a two-state characteristic, the ability to switch from one state to the other. Off, on. Cut off, conduct. Low voltage, high voltage, and so on, switching in this manner in millionths of seconds, microseconds. This two-state characteristic is the foundation of electronic digital computer operation. However, these two states and the 10 digits of our decimal number system are not compatible, cannot be easily matched. Fortunately, there is a number system that is compatible. It is based on only two digits, 0 and 1. This is the binary number system, bi meaning two. You'll hear a great deal of it in connection with digital computers. These two digits can be used to represent any number we wish. You'll find a full explanation of it in a later film. For now, let's accept the fact that a two-state device, such as a lamp, or a diode, or a transistor, can be used to count in the binary system. Off can be considered binary 0. On, binary 1. Let's add another component. Now there are more possibilities. 0, 0, 0, 1, 1, 0, and 1, 1. 3 will give us more combinations. Add more lights, and even more combinations are possible. Since the computer's language is binary, we must feed data to it in binary form. Take these binary 1s. They can be represented by holes punched in a card at keyed locations. Unpunched locations represent binary 0s. We can use cards like these as an input medium or an output medium. Special coding enables us to represent letters of the alphabet, punctuation marks, and other symbols. A single card has approximately 1,000 locations for such bits of information. Bits is an abbreviation of binary digits. The data recorded on the card are read by metal fingers or brushes that make electrical contacts through the holes, and no contacts where there are no holes. Reading may also be done by using light beams and photocells. Paper tape is a similar carrier of information. Magnetic tape, which has an iron oxide coating, is still another vehicle for information. Small areas are magnetized, shown here symbolically, in one direction to represent binary 0, and in the other to represent binary 1. Thus, problem data and program instructions carried by the tape or whatever input medium is used enter the computer in the form of a binary code. The computer is part of a system that includes input and output devices. The input device is a data reader that converts the tape or card information into coded pulses of electricity, high and low voltages that represent binary 1s and binary 0s. The computer contains storage, control, and arithmetic sections. The storage section, sometimes referred to as the memory, contains elements that receive and store the problem data and the instructions. The control section directs all computer operations. Essentially, control is a timing and gating system for transferring data. It controls input, takes each instruction from storage and interprets it, sets up the arithmetic section to do the mathematical or logical operations required, releases the problem data to the arithmetic section, and routes the results to storage. When the problem has been worked out, control routes the result to the output device. This device transfers the results to an output medium, tape, cards, printed form, or visual display. This, then, is the general scheme of operation of an automatic digital computer, midget or giant. In subsequent films, you will get to know the special meanings of such terms as word, logic, register, clock, and, or, and flip-flop. The automatic digital computer is a remarkable tool. In its many forms and sizes, it can do almost anything, but only at man's bidding. It will never duplicate the achievements of the human mind, for the computer has no initiative, no imagination, no spirit. Yet it is opening new fields of thought and work and new goals for the human race. Man has made many tools that have multiplied the power of his hands. Here is one that multiplies the power of his mind.